for which f is sensitive to dxi. Or sometimes we will write it in a more compact form, and can I squeeze that in here, if you wouldn't mind? This is a more compact form where this stands for this, and Fi1 stands for this. So this is the compact form, which is convenient to remember. Any questions about this theorem? Okay, let's now prove this theorem. And to prove this theorem, I'm going to need Shannon's expansion theorem. This is Shannon's expansion theorem. How many of you have heard about Shannon? Claude Shannon. I guess electrical engineers should know about Shannon. He came up with, let's see, what did he come up with? He gave some theorem about,
Sampling theorem.
yeah, the sampling theorem, right. So, and he did some other things. So the sampling theorem was one of his main contributions, which is actually really fundamental to
digital signal processing.
Representing of real signals using digital signals. But he also came up with this. It was the same Shannon. And so this is his expansion theorem. And it says that any function can be represented as oops, sorry about that. Okay. That makes sense. This is Shannon's, oh. So you can, this basically says that you can split any Boolean function into two parts, and in this way you can easily verify that this is correct. We will not prove it, but we will just use it. And here's the proof of this theorem. So let's look at the proof for this theorem. Now we have said that T is given as this. Now we will basically use this to prove. This is our starting point. Now we have said this earlier, and now we need to somehow arrive at this. And this is what I will do. Notice that the faulty function, and we are assuming that the fault is input xi stuck at 0. So we know that this is, Fi0, right? this here, because they mean the same things. Finality function is x of I set equal to 0. And this we can expand using Shannon's expansion theorem, and that, let us expand it using x sub I. Okay, and now we need to use a little Boolean algebra to simplify this. And okay, and using some Boolean algebra, we need to okay. Okay, so let us expand this using Boolean algebra. And let's see how much time we have. So we have about 10 minutes. And that should be enough. Okay, so let's simplify it. And that is going to be now remember that A exclusive or B is equal to AB bar plus A bar B, right? So we are going to use that, and so we are going to get now this might look a bit long, AB bar, but some of the terms are going to drop out. So it is going to turn it into a simple expression. So we got this part, and A bar B, and A bar B is this, and which is and let us simplify that. So notice that this term and this term, they are going to drop out. So we are going to be left with so I have simplified this, and I need to simplify this. So let me expand that. So that is going to be let me make sure that I have written this correctly. Make sure I don't lose any bars there. Okay, does that look correct so far? So I hope you guys are, I don't have the intermediate steps in my notes, so it's your responsibility to make sure we haven't made a mistake so far. And okay, let's double check sorry about that. This bar, so this bar plus this bar, and this bar is equal to this bar plus this bar, and that should be correct. So this term I can simplify as, so this is equal to this term so we have here, this would drop out, so I will have okay, hopefully this is correct so far. And this term is going to drop out, so we are going to left with this is going to go away, so I'm going to left with and we should be close to our result if I have not made a mistake. And let's double check and make sure that our algebra is good. Okay? And that is equal to, as you can see, and remember, this is what this is our Boolean difference. So this is our df by dxi by definition. So this is the proof. That proves that the theorem we had was correct. Any questions on this proof? Okay, so we have said that if it is x of I is stuck at 0, the tests are given by this. Now what about the case when x of I is stuck at 1? How are we going to find the tests? Well, the only difference is that, and you can prove it, df by dxi, that part is the same. So this is the part which is different. So notice that there are two factors here. At the site of the fault, excite the fault, that means at the site of the fault, bring a value which is opposite. So if the fault is stuck at 0, normally you make that 1. And create conditions so that the output is sensitive to the change in value at the site of the fault. So these are the conditions for propagating the fault to outside. And here, if it is stuck at 1, you need to apply a 0 at the site of the fault and have the conditions that will allow you to propagate the effect to outside. So the only difference is that